When a traditional ship's steel hull meets multi-year crystalline ice, the established physics of standard maritime navigation completely collapse. At -40 degrees Celsius, ocean water ceases to be a fluid, becoming a structural barricade. Standard marine steel exposed to these temperatures suffers a ductile-to-brittle transition, shattering on impact. To penetrate this environment, shipbuilders had to abandon hydrodynamic tradition. An icebreaker does not rely on a sharp, bladed bow to slice through the frozen surface. Instead, the vessel operates as a massive kinetic wedge. It weaponizes its own 30,000-ton displacement mass, using gravity, not edge geometry, to crush the ice beneath it. Executing this maneuver without tearing the ship apart requires a highly specialized internal architecture, a synchronized system of high-tensile metallurgy, extreme thermal dynamics, and hydrodynamic air lubrication. Look at the physical geometry of the hull. A standard cargo ship uses a V-shaped piercing bow designed to part liquid water. If driven into an ice field, lateral pressure would crush it. The icebreaker replaces this with a blunt, spoon-shaped bow. As the engines push forward, the inclined plane of this rounded bow acts as a ramp. Forward kinetic momentum is translated directly into vertical lift. The vessel drives up out of the water, resting its 25,000-ton weight directly onto the surface of the ice sheet. The crust breaks because the tensile strength of the ice cannot support the gravity of the ship's displacement mass. This constant impact cycle introduces a severe material constraint. Ordinary carbon steel loses its elasticity in extreme sub-zero temperatures. To absorb the shock, the hull's ice belt is forged from EH36 high-tensile steel. This exterior plating is cast up to 50 millimeters thick, supported from the inside by a dense, tightly spaced lattice of transverse structural frames. By heavily alloying this steel with manganese, engineers ensure the grain structure maintains high ductility, allowing the metal to flex rather than fracture upon impact. Even with the right geometry and steel, the ship faces the threat of static friction. At these temperatures, ice acts like an industrial adhesive, effectively welding itself to the steel hull. Engineers coat the entire ice belt in specialized low-friction epoxies, like Inerta 160. This glass-smooth synthetic layer drops the coefficient of friction to near zero, ensuring the massive structural lattice slides through the fracture zones without stalling. When encountering multi-year ice ridges exceeding 3 meters in thickness, even this kinetic wedge can lose its forward momentum, a failure state known as besetting. To escape, the ship relies on dynamic internal countermeasures. The first is the healing system. Deep inside the hull, high-capacity mechanical pumps are activated, rapidly transferring hundreds of tons of liquid ballast water back and forth between port and starboard tanks. This creates an extreme, artificial oscillation. The massive lateral wobbling physically breaks the coefficient of static friction holding the ship, allowing it to slip free from the ice channel. The second system operates outside the hull. Massive internal compressors feed high-pressure air to a subsurface bubbler system arrayed along the ship's lower flanks. As this air is forced out beneath the waterline, it violently rushes upward, creating a continuous hydrodynamic lubrication layer. This highly turbulent air-water screen physically separates the steel from the ice, reducing hull friction by up to 25%. Aft of the hull, propulsion faces a different threat. Standard fixed propeller shafts are highly vulnerable to the extreme shear forces generated by dense, submerged ice blocks. Modern architectures solve this by eliminating the internal shaft entirely. They utilize Azipods, external 360-degree steerable propulsion units mounted directly beneath the stern. When forward momentum is impossible, the captain can execute a double-acting maneuver, rotating the ship to drive the stern directly into the heaviest ice. Here, the extreme rotational torque of the stainless steel propeller blades is used to physically mill the frozen ridge. The pods act as industrial grinders, chewing the multi-year ice into a liquid slurry and flushing it backward. These active interventions provide a continuous state of motion, ensuring the hull remains decoupled from the ice shelf even when forward momentum is exhausted. Sustaining the healing tanks, the bubbler compressors, and the massive Azipods requires an energy density far beyond typical maritime standards. While diesel-electric generators can power smaller operations, navigating the deepest Arctic sectors demands nuclear fission. Vessels like the Arktika-class are built around twin RITM-200 nuclear reactors. Together, these compact cores generate 175 megawatts of continuous power. This closed-loop system is highly efficient. The extreme thermal byproduct generated by the reactors is actively routed outward, heating internal pipe networks and de-icing critical deck equipment. The result is a self-sustaining mobile superstructure, capable of operating independently in the most hostile environment on Earth for years without refueling. By mastering the precise balance between geometric rigidity, advanced high-tensile metallurgy, and the manipulation of static friction, marine architects have conquered the Arctic. This architecture operates by exploiting the same physical forces that trap ordinary ships. It is 30,000 tons of steel engineered to overwhelm the frozen crust of the planet.